Hi, everyone, and welcome to tonight's presentation. I'm happy to see so many familiar faces and new ones as well. Tonight, we are joined by Dr. Carrie Fitzgerald, physicist, Montgomery College educator, and NASA Solar Ambassador, as she brings us her exciting presentation, Planets and More Planets, on the search for the alien worlds in our galaxy. Reminder, please remain muted during the presentation, and as always, you can send any questions you have throughout in the chat, and there will be an opportunity at the end to unmute for Q&A. If you enjoyed tonight's presentation, make sure to check out our website and register to join us again next week. Without further ado, Dr. Fitzgerald, take it away.
Oh, thank you so much. So I'm just going to get my presentation started here. And first of all, sincere thanks for inviting me to speak. It is such an honor and a delight to be here. So I am Carrie Fitzgerald. I'm a professor at Montgomery College, a community college in Montgomery County. And we have 3 campuses in Rockville, Germantown, and Tacoma Park, Silver Spring. In the before COVID times, I was primarily at the Rockville campus, where we have an astronomical observatory. And once everything is open up again, I invite you all to come to one of our public observatory nights. In the normal times, I would host observatory nights twice a month where the public can come to our telescopes and look at the sky, and it is always a delight. And so I'm going to be talking tonight about exoplanets. Now, it's not my research background, it's just a subject that I'm fascinated about. My research background is actually in nuclear astrophysics. So I studied nuclear reactions that take place in stars. And so we measured in the laboratory how fast these reactions proceeded to try to understand stellar evolution. But of course, a part of stellar evolution is understanding planets. And I think one of the most fascinating discoveries of our time has been the discovery of all these exoplanets. So tonight, I'm just delighted and excited to share with you how astronomers find exoplanets and some of the current thinking in this research. So we'll get started. All right, so first of all, what is an exoplanet? An exoplanet is any planet that doesn't orbit our sun, isn't part of our solar system. And exoplanets can orbit other stars. They can also orbit dead stars or brown dwarfs, failed stars. Believe it or not, there have been findings of exoplanets around these dead stars known as pulsars. Now, tonight, I will be focusing on exoplanets around, garden variety stars, because I think that's most interesting, especially when we start to consider the question of, is there life out there besides of our own in our galaxy? The problem with detecting exoplanets is how faint a planet is compared to the star. It's really a technical challenge. The nearest stars are light years away from us, and the star itself is just billions of times brighter than the planet. So it's difficult to see a planet around a star. So it's only been recently that astronomers have been able to look for these other planets beyond our own solar system. There's 2 general ways that we're able to do this. You think the easiest way would be like, let's just take a picture of these star systems and see what we get. And that would be direct imaging of the planet or the spectra, which I'll talk about in a little bit. But this is a challenge. Like I've mentioned, the stars are very bright and very far away. So getting direct imagery is a big technical challenge. The way we've been able to get at exoplanets more commonly is by using these indirect methods. That is, looking at the star itself to tell if there's a planet or planets orbiting around the star. So using indirect measurements to reveal the planetary system. And a couple of these methods I'll focus on tonight because they have been the most fruitful in our search for extrasolar planets. All right, so one method of searching for planets is this looking actually for the star to move around the sky as a planet orbits it. So I'm going to set this into motion and I'll show you. So a star and its planets, or the planetary system, it's orbiting around the common center of mass. So a star is going to wobble a bit because it has those planets orbiting around it. And what we can do as astronomers is look for that star wobbling in the sky relative to fixed stars around it, like what I'm showing here. This is difficult though, because the stars are far away. So that little wobble that they have is difficult to detect. So not very many planets have been discovered with this method, but the hope is as the technology gets better, we'll be able to discover more methods by looking for this wobble in the sky. The other way, of course, is this direct imaging. And as I mentioned, this is a challenge because stars are so bright. So what astronomers do to get a direct image of a planet is to use something to block out the light of the parent star and then try to image the planets next to the star. And we have been able to do more and more direct imaging. I anticipate in the future that we'll have more and more of this as the technology gets better. But this has not been the primary source of our planet detection either. This has. So this method is what I'm going to spend some time on tonight because it was the first way we detected extrasolar planets, and it continues to be a strong method of planetary detection. So let me talk about this. This indirect method is called the radial velocity method or the Doppler method. And I'll just remind you that the planet and the star are orbiting around their common center of mass. The star wobbles, our own sun wobbles because of the gravitational pull of the planets around it. All right, if we're at the right angle to a planetary system, we'll see the star wobble towards us and wobble away from us, towards us and away from us. And that's what's being shown in this little video here with the rainbow here. When the star is wobbling towards us, the wavelengths get compressed. We call that a blue shift. When the star is wobbling away from us, the wavelengths get stretched out, and we call that a redshift. And we can see that. And so what astronomers are looking for is this wobble of stars to indicate that there are planets orbiting around the stars. And this has been a huge method for finding extrasolar planets. And I just wanted to share what the data looks like. So if you're an astronomer and you're looking at radial velocity or the Doppler method data, this is what you're seeing. What you're measuring is the radial velocity of the planet. That is, how fast is the planet moving away from us and towards us, away from us and towards us. And you'll see this periodic curve where the planet's moving away, then it's moving towards us, then it's moving away, and then it's moving towards us. And so you measure this over time, right? And so one wavelength here, one period here is going to give you the orbital period of the planet moving around the star. That's really useful information to have. So the Doppler method can tell us about the mass of the planet. It can tell us about the eccentricity of the planet's orbit. It's a really useful tool, and it's a very sensitive tool. Astronomers have been able to measure motions of the planets, or I should say the star's wobble, like a meter per second, basically walking speed. That's what we can measure. It's pretty fascinating. And the very first extrasolar planet we discovered was discovered with this Doppler method. And the first planet was found around the star 51 Pegasi in 1995. And I was a young sprout in 1995, and I was an undergraduate, and I got my first little internship, and I worked with an astronomer who was measuring Doppler shifts. So I think this is why planetary measurements like this are so close to my heart. It was the first thing I actually got to work on as a kid. And so what astronomers do is they measure this Doppler shift, and the first planet they found was just jaw-dropping because it was so unexpected. And it's always wonderful in science when you get something unexpected. The first planet they found orbiting the star 51 Pegasi was a surprise because it had only a 4-day orbital period, meaning it is super, super close to its parent star. And it was enormous. So imagine a planet like Jupiter in an orbit that's closer than Mercury's, right? We have nothing like that in our own solar system. when astronomers looked out for these exoplanets, they were thinking they would find other solar systems out there. Like, why not, right? But what they found was completely surprising, completely unexpected. And once they started making more measurements using this Doppler shift method, they found more objects like this, Jupiter mass planets close in to the parent star. Crazy stuff. And so they gave these objects a name. They call them hot Jupiters because they're the size of Jupiter, and they're hot because they're super close to their parent star. So we have these hot Jupiters, which was a completely unexpected finding in this extrasolar planetary search. Right, so this radial velocity method can give us some useful information about the extrasolar planets. And I want to be clear that for this method and all indirect methods, we're not looking at the planet. We're looking at the star, right? We're looking at the wobble of the star. And this wobble can tell us the minimum planet mass, the orbital period, right? Just measure that little sine wave that comes from measuring the radial velocity. And the shape of the curve gives you the eccentricity of the orbit. And by eccentricity, I mean how circular is the orbit. In our own solar system, most of the orbits are pretty circular, right? But some of them further out are a little more squished, like oval shaped, and that has a high eccentricity. So the problem is we can't get an exact mass unless we know what angle we're looking at the system. If we know we're seeing the system edge on, yeah, then we can get the mass of the planet. But if the system is tilted at all to us, right, we're still going to see the star wobbling back and forth, but we're not going to get the full wobble because it's not edge on to us. So the problem with this method is that we cannot measure an exact mass for these planets unless we know that we're seeing the system edge on. But still, it's a great method and the first method that yielded extrasolar planet results. All right. And with this method, we're a little bit biased as to what sort of planets we can see. For this radial velocity or this Doppler method, it is easiest to detect high mass planets that are in orbits around a less massive star. And I'm sure if you think about this, this will make sense, right? Because we're looking for the wobble of the star. So if you've got a high mass planet, it's going to cause a bigger wobble, right? And if the planet is close, it's going to cause a bigger wobble. And if the star is smaller, right, it's going to be tugged on harder by that planetary system. So there'll be more of a wobble, right? So it's easier to detect a star that's wobbling a lot than a star that's wobbling just a little. Right, so big planets, high mass, close orbit, and if the star is less massive, it will wobble more. So initially, in the 90s, when we started looking for these planets, we had a bit of a bias in the planets that we were seeing that was biased towards hot Jupiters, essentially, which of course we never expected to find because they were a surprise. All right, so the radial velocity method, the Doppler method is great, but there's another method that has yielded even more exoplanets, and it's called the transit method. So this is another indirect technique. Again, we're looking at the star for evidence of a planet orbiting. The transit method waits for a planet to cross in front of the star, and then we measure the dip in brightness. So this is a transit. A transit is when a planet moves in front of the star, and then on Earth, we can't see the planet, it's too faint. But what we can see is a decrease in the light from the star as the planet crosses it. And that decrease in light can tell us quite a bit. It can tell us the planet's radius. It can tell us some orbital properties. It's a useful tool. And this is an even better animation of what's going on. So what we need for the transit method is for the system to be edge on like this. And then when the planets cross in front of the star, we see a dip in the light from the star, right? And so we can also work out if there's more than one planet around the star by looking at the shape of the curve. And the shape of the curve can also give us useful information like the radius of the planet. And now we can start to get to planetary properties, which we might be interested in, right? Is this a planet that humans could live on, perhaps? Maybe. And this has been the mainstay for planetary detection. As you can see here, over 3,000 planets have been discovered and confirmed using the transit method. And many more have been discovered, not necessarily yet confirmed, but this is the mainstay of exoplanet detection, the transit method. And the transit method, by its nature, can tell us about a planet's orbit, how far away is it from its parent star, and how big is that planet. And that's useful information, especially if you combine it with information, say, from the radial velocity method. I'll talk about that in just a second. Right, so here's how it works. So here's what the data would look like if you were an astronomer looking at a transit. You would be looking at the light curve for a planet, and you would see a dip in the brightness as the planet crosses in front of the star. And because of physics and gravity, we know that the closer a planet is to the star, the faster the planet is going to be moving. And our own solar system, right, Mercury moves the fastest, then Venus, and then Earth, and the outer planets move the most slowly around our star. So if close-in planets are moving faster and far away planets are moving more slowly, you can watch the light curve and the time it takes to figure out how far away that planet is from the star. So if you have a longer dip here, it means it's taking a longer time for the planet to transit. It means the star is farther away. If it's a shorter time, it's closer, right? And we can use physics and work out how far away that planet is from Kepler's laws. We can also work out the size of the planet by looking at the dip. If we're blocking out a lot of light from the star, it means we have a larger planet. If we're blocking out a little bit of light, it means we have a smaller planet. And I'll give you something a little bit more advanced here. You'll notice that the edges of these dips are angled. It's not a straight dip. And this is because it takes some time for that planet to transit, right? So this dip is happening as when the planet first approaches the star until it's all the way in front of the star. And if we time this dip, this angle, we can work out the actual diameter of the planet, which is, again, this is useful stuff to have when you're working out planetary properties using this transit method in combination with other methods. The Doppler method is favored for those large, close-in hot Jupiters, but you can get at these Earth-like planets when you're using the transit method. It's a more sensitive method for detecting exoplanets, which is great if you want to, if your goal in life is, I want to detect another Earth, you're going to want to use the transit method and not necessarily the Doppler method, right? The most famous mission for exoplanets has been the Kepler mission, which was launched in 2008 to look for transiting planets. And it was in an orbit kind of following the Earth, and it looked for transits, and it did an amazing job. Unfortunately, it was retired, I think, in like 2018. But in the time that it was working, it found, nearly 3,000 exoplanets, pretty substantial amount of exoplanets. And since Kepler, other missions have been launched and are in the works for launch to find more of these exoplanets. But Kepler was like really strong in our exoplanet detection. Right now, we have NASA's TESS mission, which is also looking for these transiting exoplanets. And this is a sensitive mission. And it's also does rely on some citizen science. So if you are really into exoplanets, you can help NASA astronomers look for exoplanets. If you just like put in a search engine, TESS citizen science exoplanet, you'll lead to a site and it will show you how to analyze some of the NASA data. So you too can help look for transits and maybe find some more exoplanets. But what we really want to know beyond like, okay, there's planets out there. And even before we started looking, we kind of knew that there would probably be planets out there. Current theories of star formation suggest that planets are a common occurrence when a star forms. So we had the idea like, yeah, there's planets out there. But what we'd really like to know is like, well, what kind of planets are they? What do they look like? Are there planets like our own? Are all of the solar systems out there like our own solar system? So from looking at radial velocity data and looking at transit data, we can figure out things like the orbital periods. How long does it take a star or a planet to orbit a star? How far away are the planets from the star? What is the shape of the orbit? Are the orbits very circular? Are they more elliptical? We can start to work out the planet mass, the size of the planet, and the density of the planet. And that one's crucial because that will tell us if the planet's Earth-like or if the planet's Jupiter-like. And we can also too, for planets that transit their star, we can begin to work out atmospheric properties, right? What is their atmosphere made out of? And that's really exciting stuff because that can tell us like, oh, could this support life as we know it? So the best thing to do is to have data from more than one method. And for this to be the case, you would need a system that is viewed edge on so that you can get a transit. And also it would allow you to get a reasonable estimate for the mass using the radial velocity method. So let's say we have a system that's edge on because we see a transit. We can get the planet mass from the Doppler method, and we can get the shape of the orbit from the Doppler method. We can also get the orbital period. Using the transit method, we can work out the actual size of the planet. What is the diameter of this planet? And we can work out the distance of the planet from the star. All right, so this is all useful information. When we combine these two methods, we can get at the density of the planet. Right? And this will tell us whether or not the planet is rocky, whether it's Jovian and gaseous, or if it's something that we've never seen before. All right, so again, here's our Doppler method data. You study this data, you get at the mass, right? Here is our transit data, right? You look at the transit data and you get the radius. And you might remember from some class that you can, if you know the radius of the sphere, you can get the volume of the sphere, right? If you know the radius, you get the volume. And that's what we want for density, right? The density of an object is its mass per its volume, right? So a lead brick is far more dense than a balloon or a feather. And by getting the density, we can know something about what this planet is made out of. And it's exciting information to have. All right, so I just want to share a exoplanet that's pretty interesting. Well, first of all, on the bottom, I've got the planet Saturn. The Saturn's a part of our own solar system, and the density of Saturn is about 0.69 grams per cubic centimeter. And you may know the density of water. Density of water is 1 gram per cubic centimeter. That means if you had a bathtub large enough, you could float Saturn in it. Saturn would float because its density is less than water. Now, I don't know the logistics of finding a bathtub actually large enough to host Saturn, but it is less dense than water. And we think that's kind of, an interesting thing. But look at this. We've found exoplanets that are not only less dense than water, but a lot less dense than water. So this guy, HD 20948b, this guy has a density of 0.37 grams per cubic centimeter. Like, what's going on with that, right? So you could definitely float that guy in a bathtub if you had a bathtub large enough to float a planet in it. So a fun thing to do right, is to compare the planets in our own solar system to the planets that we're finding out there and see how they're similar and how they're different. So we'll be looking at things like the size of the planets, the distance they're away from the star, and their orbital eccentricities. And I think the thought was at first when we were looking for exoplanets that we would find many more solar systems like our own, where we would have these rocky inner planets, and then we would have these gas giants farther out. And that's just how you set up a solar system. With the discovery of all these hot Jupiters, I kind of threw that out. And the concern was, well, are our models of planet formation wrong? And that would be a problem because it would mean our models of star formation are wrong too. So it was a little bit of a puzzle, like what's going on? What's going on? All right, so another piece of information I mentioned that we can get from the transit method is atmospheres. And just to give you a little taste of how this is done. All right, imagine a planet like this little cartoon planet here that has an atmosphere, right? To figure out what types of elements are in the atmosphere, we use something called spectroscopy, right? We're looking at spectral lines. And what's done with this is we have a star in the background that's giving off all this light that is being pushed through the atmosphere. And when we look at this situation through a spectrometer, we get the spectral lines from the star itself, but we also get the spectral lines from the planet's atmosphere. And from that, we can work out what molecules are in that atmosphere. So that's how we can begin to understand, well, okay, we've got an Earth-like planet. Does it have argon on it? Does it have nitrogen? Does it have oxygen? We can now begin to sort that out by looking at the spectra of the planet's atmosphere. So it's good stuff. All right, so here is some data for you. So these are exoplanet discoveries up to about 2015, and I'm sure you could find something more recent online, but it's a lot of planets. All those yellow dots are from Kepler. The blue dots are from radial velocity methods. The yellow dots, of course, are the Kepler transit methods. And so we're seeing tons of planets here that are with radii less than that of Neptune. So this is the planet radius here versus the orbital period. And the reason this is kind of this weird shape is not necessarily because there are no planets out there. It's an observational bias to the methods we've been using. The Kepler mission was only up for a little over 4 years. And so getting orbital periods much longer, it couldn't do it. All right, so we're a little bit biased in what we're seeing, but we are seeing lots and lots and lots of planets, both with the transit method and the radial velocity method. But when we look at sort of what size planets we're seeing around these different stars, and this is just Kepler here, we're seeing stuff that we've never seen before. We're seeing planets that don't exist in our own solar system. So there's this, here's the planets in our own solar system. Here's Earth, and then we're going up to Uranus and Neptune. There are these planets here between 1.4 and about 3 Earth masses that just don't exist in our own solar system, but we're seeing lots and lots and lots of them around other stars. So astronomers have nicknamed the planets that are more massive than Earth super Earths. So they're not gaseous planets. They're rocky planets like Earth, but they're a lot bigger than Earth. So like I said, there's nothing like this in our own solar system. Then we've got kind of these guys out here that are smaller than Neptune, maybe have some gaseous properties, maybe a little rocky, different than anything that's in our own solar system. We're calling those mini Neptunes. And so the big takeaway here is the surprising planets that we've never seen before, planets that we didn't expect to see, right? And also the sheer number of planets. I mean, honest, I'm not sure this is such a surprise. Our Milky Way galaxy has 200 billion stars at least in the galaxy, in just our galaxy. And since it's thought that planet formation is common when a star forms. When a star forms, you get an accretion disk and you get planets. There should be lots of planets. But right now, based on what we've seen with Kepler and other transit methods that have been able to detect Earth-type planets, that there may be well over 30 billion Earth-sized planets in our galaxy. Right? That's a lot. That's a lot of planets. And then it raises the question, well, is there life on these planets? So far, we have no evidence that there's any intelligent life out there, but maybe. All right, so if we compare just on average what we're seeing in the exoplanets versus what we're seeing in our own solar system, what we see exoplanets that are close to their stars have more circular orbits. And we see that exoplanets that are far from their stars have elliptical orbits. All right. Thing is that our model of star formation and planet formation suggests that all planets should be more circular. Really, most of the orbits in our solar system are quite circular. So it's a little bit of a puzzle that we have these elliptical orbits in these exoplanetary systems. So that leads to some unanswered questions about our theory. The current theory of planetary formation is called the Nebular Theory. And the idea is that stars form from these molecular clouds of gas and dust in the disk of the Milky Way. So there's a huge molecular cloud, and usually there'll be some sort of mechanism to fragment the cloud, like a nearby supernova or some starbirth or something. The cloud fragments, and then all those little fragments become stars. Material starts condensing, spinning around, so you get some angular momentum built up. They wander away from one another. And as the star spins, so you get the angular momentum built up, you get an accretion disk around that protostar. And in that accretion disk, you get planetary formation. And in theory, you should get rocky planets on the inside, gaseous planets farther out, and the orbit should be about circular. Right. But clearly, when we look at our exoplanetary systems, we see things that don't look like that. Right. Now, some things do match up. Right. We do see that planets are a natural consequence of star formation. We're seeing lots of planets. It would be worse if we didn't see any. Then we would be like, oh no, our model of star formation and planet formation is wrong. But no, we're seeing lots of planets. That's good. We also see that if you have a nebula with more rock and more ice, you can form more planets. A lot of the stuff is making sense, but there are these couple of things that don't, like the hot Jupiters and the elliptical orbits and sort of these weird planets that we don't have in our solar system. So the question is like, where did that stuff come from? Like, why don't we have that? Why do these other solar systems have that and we don't? So the model we have been using for planet formation predicts that Jupiter planets should be formed far away from their stars, not nearby. But of course, we found all of these hot Jupiters that defy that. It's a question, what's going on? Is our theory wrong? Like, what did we do? Nah, probably not wrong. So the first question is, can these Jovian planets form close to their stars? Probably not. It's too hot to form a gas giant really close to your parent star. Probably not can happen. But what you can get is your planet formed way out in the edge of your system, and then it migrates inward. So what we're seeing is the result of Jupiter planets formed far away from their stars, but they've migrated inward because of density waves in the protoplanetary accretion disk. So the idea is, when things are just beginning when a star is formed and you have this disk, it's really, really messy. It's like there's rocky stuff all over the place. You can get these density waves set up, and you can have a hot well, it's not hot when it's way out there, but you have a Jupiter migrate inward and turn into a hot Jupiter, right? And so here's an artist's rendition of a hot Jupiter, or a Jupiter about to be a hot Jupiter migrating inward. And in our own solar system, it's thought that our outer planets have migrated somewhat. That where's like Jupiter and Saturn are, they weren't always there. They have moved somewhat. So in the end, we don't really need to completely rethink our theory of planetary formation. We just need to tweak it a bit and need to understand that different stars, different protoplanetary disks are going to have different conditions. And we can get planets that are really diverse and unusual, right? And so I want to talk a little bit about those unusual planets. They're crazy. They're amazing. There's a much wider variety of planets than we originally thought. Like here's another artist's impression of a super Earth. And these are planets that are more massive than Earth. We also get a class of planets that aren't quite Earth-like, aren't quite gas-like. This is an example, GJ1214b, which could be some sort of water world. Not sure what's going on with that water world. And then we have planets like this. So this is a planet that's twice the size of Earth, but 8 times more massive. So a really, really dense planet, mostly carbon. And so think about this. It takes 18 hours for this planet to make one orbit. So a year for this planet is 18 hours. So it's really, really close to its star, right? That's pretty crazy. All right. So this is one of my favorites of the exoplanets. I guess I just like the name. So we found more like this. So this is an extremely low density planet. So this is a planet that has the density of like a wine cork. And they're called Puffy Planets. So these Puffy Planets are larger than a Jupiter, but really, really low density. So you've got this enormous planet with a density of cork hanging out, this Puffy Planet. But it does lead to this question. What does this say about our own solar system? Is our solar system unique? Is there any other system like our own? And if there's not, then what does it say about the possibility of finding life in the universe like us? Not to say that we're like the most intelligent life, but we haven't really found consciousness in the universe yet, right? We haven't received any signals to show that there's somebody else out there besides us, despite the fact that there are all of these planets, billions of planets in our own galaxy, right? So this is a pretty famous system that Kepler found. It's the TRAPPIST system, and it has 70 Earth-sized planets, about 40 light years from Earth. And some of those planets seem to be in a zone that would allow for liquid water. And so the question is, like, maybe there could be life there. Haven't heard from it yet, but maybe. But bottom line with exoplanets is that they are abundant and diverse, and we're going to continue to find them as more missions go up. You may have heard of the James Webb Space Telescope, which, fingers crossed, because it's been delayed so much, is due to launch this coming December. And if James Webb launches, hopefully it will launch then, James Webb is going to be looking for exoplanets, and is going to be looking for transits, and is going to be looking to take spectra of those exoplanets. So we might have some really big discoveries in the near future when it comes to exoplanets. All right, so before I set you all loose with questions, I want to mention this. I mentioned this to just about everyone who knows me, Stellarium. So if you are interested in like, well, what planets can I see in the sky tonight? Or what can I see in the sky tonight? You're not going to be able to see any exoplanets, but you can see planets in our solar system. And the tool that I use nearly daily is a free web-based tool called Stellarium. You can use it on the web or you can download it on your computer. It is free. It's how I do all my astronomy labs for my students. And so I highly recommend it. There's a mobile version for your phone, but that costs a few bucks, I think. So I'm going to recommend, if you are like excited about looking in the night sky, that you download Stellarium. And I can put this link in the chat. So I want to share one more thing. I'm going to share my Stellarium for you. And this is to give you a sample of what it does. So this is showing us the local sky tonight. And you can see it is a wonderful time to go out and look at planets. So right now, what time is it? It's about 7:44. Venus is about to set, but Jupiter and Saturn are still out. If you go out tomorrow a little bit earlier, Venus will be a little bit higher. And the nice thing about Stellarium is you can change the date and time to anything. So if you are like really curious about, say, what was the sky like in Egyptian times, just because it's fun, you can go to like 3000 BC if you want, or you can go to like 26,000 BC, right? Or sorry, 26,000 AD and see what the sky will look like in the future. You can go to any location on Earth, any time of night, anywhere, and look at the sky. So highly recommended for figuring out what's out in the night sky, and it's completely free. So that's Stellarium. Right. So I will take a look at the chat, see if there's any questions here. Oh yeah, I'm seeing that people don't know that there is an observatory. Yeah, it's frustrating. People don't know there's an observatory and that we're open to the public. I mean, not now because of COVID, but the campus is supposed to be opening next semester. And we've just installed some new equipment. It's a great time to get out on the roof. And if you guys as a group want to come as like a special night just for you, we can totally do that. We do special nights for people. I see another question about viewing the system edge on. Well, really the only way to know if you're viewing the system edge on is to either see that transit, see a dip in the light, or if you're seeing the wobble, you know that it's somewhat edge on. To confirm it's completely edge on, you need the transit. So that's unfortunately the only way you can get at it. Observatories or planetariums in the area that are open. Oof, that's a tough one. I think stuff is starting to open up again, but most places have shut down for COVID, especially the planetariums because it's closed in. There are 3 amateur astronomy clubs in our area. So they might be starting events again since they're outside. There's the Northern Virginia astronomers. There's the Capitol astronomers in Washington, D.C. When they observe in Rock Creek Park. And then there's the Greenbelt Astronomy Club. They've got a little telescope in Greenbelt. So you can check to see if those guys have started up again. And I'm really excited that you guys want to come to the observatory when we're open. I would love to have you and meet you all in person and share the sky with you. Any other questions that I can answer?
I see another one in the chat, in private chat, that says, do astronomers think all stars are equally hot, or does each star have individual properties?
Oh, that is an excellent question. Yeah, the stars have different temperatures. So when stars are born, they're born with different masses, and the mass of the star is fundamental to what happens to the star. So stars can be born with a high mass and they'll be very, very hot. And when we're talking about temperature, the temperature that we can see from Earth is the star's surface temperature. All stars are hotter at their cores because that's where the nuclear fusion takes place. So when you go outside, let me see if I can get us back to like 2021 instead of like the far future. When you go outside tonight and you start looking at all of these stars, you're going to notice that the colors of the stars are somewhat different. Some of the stars are going to appear really white, and some of them are going to appear kind of this golden color. And that color has to do with the temperature. The more red the star is, the cooler the star is. If a star is blue, it's very, very hot. If a star is red, it's not as hot. Most of the stars, though, in our galaxy are cool stars. So just population-wise, if you're taking a census, most of them are cold or red stars. All right. Any theories on why the great number of mid-sized planets in other galaxies? Yeah, so we're still working out what the gap is, like why we're seeing the number of planets that we see with the number of sizes. So I think that's still an open question. As far as like, we've only been able to look at planets in our own galaxy. So we're making the assumption that planets in other galaxies would be similar, and that star formation, everything else is similar. Not sure if that helps you much, but maybe.
I've got a question for you.
Sure.
So, and I apologize, this is going back to maybe when I was in 6th grade and many, many years ago. But I remember learning that as stars age, they grow. And as they're growing, they swallow planets closest to them up until they reach a point where they go supernova. Could any of those super Jupiters be orbiting an old star, and they're about to be swallowed up?
Yeah, absolutely. So most of the stars that missions like Kepler and TESS have targeted have been stars that are not about to blow. So we call those stars main sequence stars. They're stars like our sun that are really stable and they're not about to go supernova. But that doesn't mean that there aren't planets around stars that are more near the end of their lives. In fact, I would bet that there are lots of planets around stars that are about to go supernova. Now, the issue is, like you're saying, you're exactly right. When a star reaches the end of its life, it gets larger. It turns into a giant star or a supergiant star. And if a planet is near, it's going to get swallowed by that star's atmosphere. In our own solar system, in about 5 billion years from now, our sun will become a giant star, and it will swallow Mercury and Venus. And basically its outer layers are going to swallow, or just like maybe not swallow Earth, but like be right up to Earth. So you can imagine like watching the star's atmosphere. It's going to be right on top of us. And then, of course, after the star ends, our star won't have a supernova. It will be a less violent death, but it will shed its outer layers in an explosion and, take the solar system with it. But yeah, once that happens, it's kind of over for the planets. And that's a really good question you raised too, because if we're thinking about life on other planets, it would be best to look at stars that have longer lives. So really massive hot stars don't live very long. They live on the order of millions of years instead of billions of years. So if it takes as long as it took us to evolve on other planets, like we want life like ours, looking around a hot star isn't going to be the answer, because that star is going to blow up before intelligent life can evolve. Again, not that we're like super intelligent or anything, but we do all right.
Well, thanks.
No, thanks for asking.
Do we have any further questions? Feel free to either unmute and ask them yourself at this time or send them in the chat. Well, I would just like to point out, I just put in the chat a resource from Dr. Fitzgerald that links to a current star map for our area. So if you'd like to click that, it'll download a PDF file for you if you're interested. Thank you so much for joining us tonight. I hope you all enjoyed tonight's presentation as much as I did and learned something new. Of course, if you think of any questions later, you can always email us at info@poolesvilleseniors.org and we will pass them on for you. And of course, when MC Observatory reopens, we will absolutely be planning a field trip.
Yes.
If you'd like to unmute or turn on your camera now to say goodbye, now is the time. If you're joining us on Facebook Live, please leave a like and a comment. We'd like to thank Dr. Fitzgerald for this presentation, as well as our ongoing sponsors and private contributors that help us keep our programs going, because we love putting them on for you. If you enjoyed tonight's program, please consider joining us for more upcoming events. This time next week, we'll be back with our Veterans Day program. You can go to our website, poolesvilleseniors.org, for more info and registration. Thank you all so much for attending. I hope you have a wonderful evening.
Oh, thank you so much.
Thank you.